My name is Srinivas Arun, and today I'll be presenting the solution to the OMMC August problem of the month. So the problem says the positive integers are partitioned into two infinite sets, so the sum of any 2023 distinct integers in one set is also in that set. And we want to prove that one set contains all the odd positive integers and one set contains all the evens. So let's start by rephrasing what we're trying to prove. So we want to show that one set contains all the odds and one set contains all the evens. Or in other words, that every set contains every other element. So it's natural to first try to prove that no two elements can be consecutive in the same set. So for all x and x plus 1 cannot be in the same set. Because we want to show that every other element is in the set, so it makes sense to prove that no two consecutive ones are in the same set. So for the proof of this, we assume the opposite. So assume that x and x plus 1 are in the same set. Now, the sets are infinite, so we know there are many other elements in the set. So let's call those A1, A2, A3, and so on. And now we have to use the condition that the problem gives us, which is that the sum of any 2023 distinct integers in one set is equal to another element in that set. So this might be a little difficult to wrap your head around because it's really hard to think about 2023 terms at once. So instead what we can do is we can think of 2022 terms. We can just fix those terms. So let's say there are some 2022 terms that have a sum. Then we know that that sum, if we add it to any other element, must be in the set. Because any other element plus those 2022 elements that we fixed is a sum of 2023 elements. So this motivates looking at a sum of 2022 elements. So let's consider the following sums. First, we have x plus a1 plus a2 plus all the way to a2021. And since we know that x plus 1 is in the set, that's what we're assuming. We also have that this is in the set. Or sorry, these are not in the set, but these are both sums of 2022 elements. And that means if I add any other element of the set to either of these, then I'm going to get another element of the set. So let's call this S, and let's call this S plus 1 because it's just one more than the previous sum. So if I consider some element of the set, let's say M. But we also have to assume that M is distinct from any of the numbers that we've already worked with because we want 2023 distinct elements. So let's just say distinct from everything above. Then M plus S and M plus S plus 1 are in the set. This is because M plus S is a sum of 2023 distinct elements, and also M plus S plus 1 is a sum of 2023 distinct elements. So I know if I have any element of the set which is distinct from all the ones I've written down, then I can add S to it, or I can add S plus 1 to it, and still end up with a number in the set. So to generalize this, I can actually get M plus any linear combination of S and S plus 1 is in the set. This is because I can keep repeating this claim from the previous slide. So I can get m is in the set, then m plus s is in the set, then m plus s plus 1 is in the set, then m plus s plus 1 plus s plus 1 is in the set, and so on and so forth. And continuing this way, I can get that m is m plus any linear combination of s and s plus 1, which basically means a multiple of s plus a multiple of s plus 1 will always be in the set. So now that we have this, we're actually ready to finish the problem. Because this linear combination should remind you of the chicken McNugget theorem. So I'll just briefly go over what that states. If m, or let me use a different variable, if p and q are relatively prime, then the greatest integer that can't be written as a linear combination of p and q is pq minus p minus q. Now this is not hard to prove if you just look at, it's pretty easy to find a construction for all numbers less than this, all numbers more than this, and it's pretty easy to prove using remainders that all numbers less than this can't be expressed. But in fact, we don't even need like the full power of this theorem. All that matters, all that we're going to use is that all numbers greater than pq minus p minus q can be written as a linear combination of p and q. So in other words, all sufficiently large positive integers can be written as a linear combination of p and q. So let's go back to the question. So we know that m plus any linear combination of s and s plus 1 is in the set. But as we just said, all sufficiently large numbers are linear combinations of s and s plus 1. So what this means is that m plus all sufficiently large numbers is in the set. And since m is a constant, that means that all sufficiently large numbers are in the set. So let's think about what we've proven. We've proven that after a certain point, which might be really big, after a certain point, so 1, 2, 3, 4, like at some point over here, let's say we have a number like c, at some point, all of these numbers here are going to be in the same set. But when we go back to the problem, it says that the two sets must be infinite. So even though this one set might have all sufficiently large numbers, that means the other set is restricted to only these. Other set can only contain these. But c is a constant, because remember, for all sufficiently large numbers, they're in the same set. So therefore, the other set has only finitely many elements because it's bounded. And that means we've reached a contradiction, because we've proved that the two sets cannot both be infinite. So 1, so having reached this contradiction, we go back and we can prove this original claim, which is that for all x, x and x plus 1 cannot both be in the same set. Now we're still not quite done, because even though it intuitively felt like this should imply the claim, we haven't really rigorously proved that yet. So let's do that. So let's use our claim. So we know we're assuming, or we're not assuming, we know that no two consecutive numbers are in the same set. Okay, so now let's call the sets A and B. Now let's consider some element of A. Let's say A is in A. Then we know by our claim that A plus 1 is not in A. And since A plus 1 is not in A, it must be in B. That's just from our first claim. We can't have both A and A plus 1 in the same set. So A plus 1 has to be in B. Okay, now let's look at A plus 1 and A plus 2. We know that since A plus 1 is in B, A plus 2 cannot be in B, so A plus 2 must be in A. This again is using the exact same logic. We can't have two consecutive numbers in B, so A plus 2 has to be in A. And so we've shown that for any element in A plus 2 is also in A. And what this means is that both sets contain every other element. One set must contain 1, 3, 5, 7, and so on. And one set must contain 2, 4, 6, 8, and so on. And that's exactly what we wanted to prove, and we're done. So let's go back to the problem. Using what we wanted to prove, which is that one set contains all the odd integers and one set contains all the even positive integers, we were able to conjecture this claim that no two consecutive elements are in the same set. Then, using contradiction and using the simplification of the problem by fixing 2022 numbers and looking at their sums, we were able to show that there exists S and S plus 1, such that if M is in the set, then M plus S and M plus S plus 1 must also be in the set. Using that, we got that M plus any linear combination of S and S plus 1 must be in the set. And then using Chicken McNugget theorem, we got that M plus all sufficiently large numbers, which basically means all sufficiently large numbers, must be in the set. And finally, we used our claim that no two consecutive numbers are in the same set to prove that if A is an element of one set, then A plus 2 must also be in that set, which easily implies that the sets are the odds and the evens. Thanks for watching.